Hello. Today we're going to be we're starting a new unit, aren't we? And this unit's got a lot to do with linear relations and a lot of change. So the first thing we're going to do today is talk about what is changing, who's changing, where is changing. Let's have a look, all right? So first things first, just having a look at these. Can you decide which one of these affects the other? Which one of these causes the other to happen? Have a quick go and I'll go through it. Okay, so if I'm looking at blood sugar, I'm looking at the idea of, does blood sugar affect how many energy drinks there are, or does energy drinks affect what is going on with my mic? Not my mic, my thing. Yes, that plane. Thank you. So what affects which? So if you agree that if you drink a lot of energy drinks, your blood sugar will be affected, then you agree that energy drinks are affecting blood sugar, right? So your blood sugar is affected by energy drinks, and energy drinks affect blood sugar. If you're thinking about grades in class, your grades in class don't affect the amount of time you study, or well, it might, but that's because you might get in trouble and then might want to study more. But in general, the amount of time studied affects the grades in class, doesn't it? So if you spend a lot of time studying, you tend to get better grades. If you don't spend a lot of time studying, you don't get as good grades. Obviously, it's not a linear relation, but in general, that's the kind of thing that works. Your length of your headache, does that affect if you take an aspirin or not? Well, no, it's an aspirin. If you take an aspirin or you don't take an aspirin, that will change how long your headache is done, right? So if you don't take an aspirin, obviously your headache might last longer. If you do take an aspirin, it does. That is the whole point of an aspirin, right? And last but not least, the temperature outside, does that affect the amount of ice cream sold? Yes, because the amount of ice cream sold doesn't affect the temperature. If I happen to sell 100 ice creams to my friends, that doesn't make it hotter outside, right? But if it's hotter outside, I might be able to sell more ice creams. So this is affecting this way. And if you understood that whole concept of what affects something else, you understand the relationship between dependent and independent. That's good. Yep, that's what I want. I feel like every other week they upgrade or update the thing, and it's just not better. Like every single day they update this PowerPoint. It just works worse. Okay, so dependent versus independent then. So when we investigate a relationship between two sets of numerical data, we identify two types of variables. The independent variable is the variable that affects the value of another variable. So as we just seen a second ago, the temperature outside affects the amount of ice cream sold, right? So the dependent variable is a variable that is affected by some other variable. And if you think about your life, if I call you a strong, independent woman, it means you're not affected by other things, right? Right, but you might affect other things. If you have a parent, guardian, or whatever it is that you might have at home, you officially are their dependent. So if you're their dependent, then you are dependent on them. You what their rules are affect you, right? So these kind of words are the same kind of words we use in real life. It's the same real stuff, right? And weirdly enough, as you can see, the dependent variable depends on everyone else. I don't know what's going on. I'm so sorry. I promise it's me just trying to teach. So the dependent variable depends on, and that's really crazy, isn't it? So that's how we got there. Okay. The independent changes the very dependent. Great, fantastic. So, another example. The height of a tree depends on the age of a tree. Well, the age of the tree then must become the independent variable, right? And the dependent variable, because it depends on the age, is the dependent variable, the height of tree. The amount of ice cream sales depends on the temperature outside. So again, the temperature outside is the independent, and then the amount of ice cream sold is the dependent. Okay, I know it's frustrating, isn't it? Because they sound so similar, especially with my accent as well, doesn't help. But hopefully you get the idea. Dependent variable depends on the independent, and the independent just happens no matter what. Temperature happens no matter what. The age of a tree going up happens no matter what. But the height is affected by the age. Okay, so very quickly, which one do you think's which? Have a quick go. Okay, so hopefully test scores and hours spent studying, hours spent studying. Hopefully you agree that hours spent studying is your independent, hours study, which is what I'm going to write. And then your test scores are what's affected, isn't it? So the amount of hours you study affects your test scores. What about hours worked and earnings? Okay, well, hours worked affect your earning, right? In general, if you work for 2 hours, you might get paid $30. If you work 3 hours, you might work $45 or whatever. So as your hours worked goes up, your earnings go up. So hours worked. So hours worked is your independent. and earnings is your dependent. Now, what I will also say, I suppose say earnings, if I could write, that'd be dangerous. What I would also say, if you're ever in doubt of this, anytime you see hours or time, that tends to be your independent, because time happens without any of us really having any control over it. And so therefore that is the independent. And then dependent would be like whatever time is affecting. Okay, the relationship. So the relationship between the independent-dependent variables can be shown through a table, a graph, and an ordered pair, and also an equation. But we're going to get that to like in a few lessons, so no worries about that. So let's have a look at how they're done. In general, they always go independent-dependent. Independent is the first thing you should see, and then dependent is the thing that's the next thing. So for example, in a table, the independent variable is always the first. That's either on top, or it's the first column, or it's either whatever you see, right? So for example, independence on the top, dependence on the bottom, or independence on the left, dependence on the right, right? That's how we do tables, because it only makes sense that way, right? We the independent changes the dependent, so we'd always look at that. And even if you look at this top example here, you can see that again, time was on the left. So time's your independent in general. That's probably where it is. What about a graph? Well, in a graph, we have two axes. We have the x and y. Which one comes first? X, because of alphabet. So again, that's your independent. So the independent variable is always on the x-axis. Dependent variable is always on the y-axis, right? This is always the independent variable. And look, time, again, dependent on the left, right? And the reason for that, again, x, y. What about an ordered pair? Would you believe? X, Y, independent, dependent. There are a bunch of different names for them. Domain, range is something you'll see a lot in grade 10 and grade 11. Independent variable, dependent variable is what we're saying now. X-axis, Y-axis is probably what you heard in elementary school. First coordinates, second coordinates, again, same kind of thing, right? But in general, independent, dependent, right? Independence the first coordinate, dependence the second coordinate. Rate of change then. So we can't really talk about anything we've said so far, independent, dependent, without talking about rate of change. This is when the change in one quantity is relative to the change in the other. So we will require units, but for example, it has your dependent unit per independent, right? Seconds, independent. So dependent per independent. And in general, whenever you see per something, or per like meters per second, kilometers per hour, wage per hour, or whatever you see per second, this is your independent, this is your dependent. So kilometers per hour, dollars per hour. I know, can you see how I kind of ran out of ideas of what, basically everything comes down to time. Cool. So rate of change then. Now, rate of change in general can either be positive, negative, or zero. And what I mean by that is, as one goes up, it either causes the other to go up, it might cause the other to go down, or it might have no effect whatsoever. So here's a graph that shows this one. As you can see, as our value on our x, our independent, goes up, our dependent also goes up, right? We can see it here. As this one goes up by 1 second, this goes up by 10 seconds. So this is a positive relation because it's going up. If going up is a positive, weirdly enough, going down is a negative. You'll see this one is a nice straight line, and this one isn't. It isn't, but it doesn't matter. It's still negative, right? Still negative, still positive. And the reason we say positive and negative is because as we read left to right, because that's where in the Western world, right? Read left to right, is it going up or down? And that's effectively it. And then last but not least, zero. We can have no correlation whatsoever, right? I can be like, hey, how tall is that, that tree? And then count it in seconds. And weirdly enough, the seconds don't affect the height because that's it. The height has now been there forever. Like that's 25 meters tall, 25 meters long, tall, whatever. You get the idea. So positive, up, negative, down, zero, straight across. Cool. So quick go then. You go gadget. I'll go through this in 10 seconds. Okay. So I said say 10 seconds. It'll be as long as I can to work out how to press the pen button. There we go. So just a quick way to determine whether the relationship shown on a graph has a positive rate of change, negative rate of change, or a zero rate of change. Positive go up, negative go down, rate of change zero goes across. That's supposed to be a straight line across. That's it. That's all you're looking for. For each of these following graphs, state whether it's a rate of change of positive, negative, or zero. Positive, zero, negative, positive. Doesn't matter that it's making a curve. It's still positive. It's still going up. Okay, so as you just seen in the last one, rate of change can actually be something called constant or non-constant, also called sometimes linear or non-linear. Linear or non-linear. And I think we've talked about this before, but if we haven't, let's have a look. So, can I get off this? Yes. So constant then. Constant, as you can see here, right, for every one this goes up, that goes up 1, that goes up 1, this goes up 10, right? And it keeps doing that. So it keeps going up 10, it keeps going up 10, right? So for every 1 second time goes up, height goes up by 10. It looks like this. And if you joined up all the points and you joined up any points that's on it, it should be a straight line. If I could draw a straight line, I'd be dangerous. What about nonlinear? Well, let's have a look. Every single one, this goes up 1 every single second. This goes up 10, then it goes up 15, then it goes up 20. As you can see, that's not constant. Constant would be it go up 10 each time. I can see that it goes up 10, 15, 20, so it has a gap of extra 5 each time, but that's still not constant. And if we see what that looks like, probably not the best graph I've ever grabbed off Desmos, but if I could, yep, you can see me pressing the button, right? Right, if you drew that, and even if you tried drawing them straight, you would see that that's not straight, right? That's a curve, and that's called non-constant. Okay, so quickly have a go. Okay, I'm hoping, we're going over the same kind of example over, but I have to do this, right? This is constant or linear, constant. This is non-constant, non. This is obviously non-constant because it's crazy, and this is constant. And if you really wanted to show off, you would say this is positive, this is negative. I'm not saying anything about that one, and this is negative. The reason I'm not saying anything about C is because it's positive, and then it's negative, and then it's positive, and even at these points it's 0. It's a complicated question, but if you want to know, this is actually called a sinusoidal wave. It's just, if you ever looked at your calculator and seen sine or cos or tan, if you type in sine or cos into Desmos, you'll see that it makes this kind of wavy kind of thing that happens. Okay, right, so we're going to go through some extra question together, and then we are gonna we're gonna go through a bunch more. So again, we'll see how this goes. So this one I'm gonna go through, hopefully makes sense, kind of like an example, but you can pause it here if you want to have a go and see if we get the same answer. And then I'm gonna go through the others, and that's it, we're done. So why do you think some line segments on the graph are steeper than others? So let's first of all read it. So Billy's mother sends him to the corner store for milk, right? And then tells him to be back in 30 minutes. Examine the graph and describe Billy's progress. So let's have a look. So this says time on the bottom. So obviously time's going up along the bottom. This says distance from home. So it means that the higher the line is away from home, the further away he is from home. So what he's done here then is obviously for the first 4 minutes, he's gone 200 meters from home. Then in the next 8 minutes, he's done another 200. And then in the next, 4 minutes? Next 4 minutes, he does another 300. Then I guess he's at the shop because he stops here for a bit. Then he slowly walks for a bit. He walks, 100 meters in, 8 minutes? 100 meters in 8 minutes. That man is dawdling. And then he's like, it's 28 minutes. I got told I should be back at 30. And he's rushed back, hasn't he? He's rushed back as soon as he can. And then he got home at 40 minutes, so he's 10 minutes late. Let's have a look at this graph then, like the questions. So what... Yes, I would like to press the button now, please. Yes, that button there. Yeah, if you could press that button. Thank you, there we go. Why do you think some line segments on the graph are steeper than others? Quite literally, different speeds. Different speeds. Right? He's walking different distances in different amount of seconds, right? Some of these are really fast, some of them are really slow. Like this one here, incredibly slow. Over which intervals is the rate of change positive? In other words, in which intervals is it going up? So A to B, B to C, C to D, isn't it, right? A to B, B to C, C to D. Over which intervals is the rate of change negative? That's E to F and F to G. And F to G. When is the rate of change 0? And that is DE. DE, and the rate of change is 0 because he's not moving. When is the rate of change constant? And this is one of those trick questions because it makes you think that when is there only one? It's always constant, isn't it? From A to B, it's a straight line. From B to C, that's a straight line. From C to D, it's a straight line. Even DE, that's a straight line. EF and G and F to G. In between each segment, it's constant. Each segment is constant. Right? We would look for something that looks like that if it wasn't constant. How long did Billy take to get to the store? We're assuming the D is the store, right? That's when he gets there. So all we're doing is we're just looking down to see how long that took. And I believe that is in between 12 and 20, which is, I hope you agree, that's 8 minutes. So exactly in the middle would be 4. So add 4 onto 12 to get 16. 16 minutes. How long did Billy stay at the store? He went from D to E, so that's 16 to 20, so that's 4 minutes. When did Billy leave the store to head back home? That's E, isn't it? So that's going to be the 20th minute is what I get. And did Billy make it home in 30 minutes? No, he made it home in 40. Cool. So hopefully that makes sense. Hopefully that's wonderful. And as you see in the next slide, I do quite literally say there are a ridiculous amount of questions. What I've done, and I've said it here as well, I would go through all of these and make sure you understand it. Really, because a lot of people who don't do the work now really struggle in the next few lessons. So I would really, really go through all these questions. And obviously I am as well. I'm going to go through a few. But just have a go and have a go at this. Make sure you understand. So have a go at this one. We'll go through it very shortly. Then I'll go through this one. Then I'll go through this one. And you get the idea. I'll try to go through all these. It's going to be a bit of a long lesson, I'm sorry, but you can pause this as we go through, right, and take breaks and stuff. I can't. Right, here we go. So I've got this one, and then I'll go through it. Okay, so the graph on the right shows Greta's distance from home in meters for the first 10 minutes of the evening. Is Greta moving towards home or away from home? It says in the question, it's Greta's distance from home. Yeah, so as distance goes up, that's her moving away from home. So she's moving away. And if you were going to write down an explanation, you would say in the graph it says distance from home, so you would say that. How far from home is Greta after 6 minutes? So go up at 6, go across, and you get 540. Is Greta increasing her speed, reducing her speed, or maintaining a constant speed? Is it a straight line? It's a straight line, so she's maintaining a constant speed, right? If it was increasing her speed, she'd be doing that, and if she was decreasing, it would be that, right? Because it would be slowing down. What unit would be used to describe rate of change here? As we talked about before, rate of change is just dependent per independent. So it's quite literally meters per minute. And you can write meters per minute instead of meters/minute. Is the rate of change positive or negative? Is it going up or is it going down? It's going up, so it's positive. How would the graph look different if she was moving in the opposite direction? Well, assuming she's coming home, this is one of those silly questions where the wording's not quite precise enough. Assuming she's away from home and coming towards home, it would look like that. But if she was still starting from home and moving away from home, it doesn't matter what direction she goes in, it would still look the same. So it's a bit of a silly question here, and I promise I'll make sure none of my test questions are like that. What are the independent and dependent relationship? Independent is going to be time, and dependent is going to be distance. And again, if you're not 100% okay with that, this is always the independent, and weirdly enough, the one on the side is always the dependent. Okay, next one. Have a go. I'll go through it shortly. Okay, the graph on the left shows the amount of liquid in a 2-litre container. Describe how the amount of liquid in the container is changing. So again, volume of water is on the left, timers on the on the bottom, and it literally has times going up, and then the volume of water is increasing, isn't it? So describe how the amount of liquid in the container is changing, going up. Don't say going up, but you know what I mean. Write a sentence, it's going up. How long does it take to fill the container? It says 2 litres here, it says 2 litres here, so therefore we know it's 17 seconds, because at the end you can see 17, can't you? 17 seconds. What unit would be used to describe the rate of change? Again, it's just litres per second. If you want to write per second, that's fair. Describe what happens to the rate of change of liquid in the container when the time is 10 seconds. At 10 seconds, right, the rate has increased, hasn't it? So it was going up slowly, if you will, and then it went up a lot quicker. So it was a rate of change increased, What could have happened there? There's so many things. Could have increased the amount of water being put in there. Could have put an extra faucet on /tap. You could have, I don't know. Like anything that would ever increase the rate of change is a perfect answer there. Just more faucets on, or the tap was turned on more. What are the independent? Independent, again, independent is time, and dependent is going to be volume of water. Volume. Okay, next one. COVID, always good to see. Let's have a look. Have a go. I'll go for it. Okay, the table on the right shows the number of new COVID-19 cases in Ontario over 5 consecutive days in August 2021. Here it is, just in case you can't see it. Describe how the number of cases changed over the 5 days. So, I mean, let's be like, something very simple as it's increased is more than reasonable, right? It's increased and it's non-linear as well, as what I'm talking about, because this is that's 134, is that? 174, I think that is. And then it goes up by 18, and then it goes up by 103. But the point is, it's not going up by the same amount, so it's increasing, non-constant. You throw those words at me, I'm going to be very happy. What was the rate of change, positive or negative? Positive's going up, positive, right? These are going up one by ones. These are going up by random numbers. Was the rate of change of new cases constant? No. I feel like A, B, and C are the same question. And what are the independent, dependent? Literally, read it left to right. Day is independent. Day, dependent, the amount of cases. Cool. Next one. The graph on the right shows... Oh, sorry. You have a go. Okay. Yeah, just pause it. Like, do you know what I mean? Right. The graph on the right shows how outside air temperature is affected by altitude. Describe how the air temperature changes with respect to altitude. Quite literally, when it says describe, the way I do this is I say, as something increases, so in our case, altitude, as altitude increases, what happens? That's supposed to be increasing. It's really hard to write with the pen I'm using today. And I mean, it's increasing, right? Because 1,000, 2,000, 3,000, it is going up on the bottom. What's happening to the left-hand side? Temperature is going down. Temperature decreases. Decreases. There we go. Is the rate of change positive or negative? It's negative, isn't it? It's going down. Is the rate of change in the sample constant? Is it a straight line? Yes. And you would say straight line, right? And is it negative because decreasing, if you want to know like the actual language. Identify the dependent variables. Independent in this case is altitude. Dependent then is weirdly temperature. Okay, and then I think the last one, and these are all your like level 1, level 2 questions, right? And then we'll go to level 3, level 4 after this. Right, have a go. Okay. The graph on the left shows the population of a small town over time. Describe how the population is changing over time. Increasing. Or I guess for describe, I should say, as time goes up, as time goes up, population increases. Population increases. Is the rate of change positive or negative? It's positive. It's going up, innit? Is the rate of change, example, constant or non-constant? It is not a straight line, so non-constant. And you would say non-constant, and then you would say not a straight line. Identify the dependent and independent. Independent is time. Population is dependent. Population, thank you. Why do you think a dash curve was used here instead of a solid curve? This is kind of like, if you don't know this, it's kind of like a hard question to understand. But when we do like population questions, or like in real life, when we ask people about population, we don't ask the population every single day. We take it at random times. So we know the population, for example, a starting time was, let's say it's 800. Then we know on the first year it was 1,000. Then we know at 2,000 it was whatever that is. But what we don't know is what 1.5 years was. We assume it kind of goes up in this curve, but for example, between 4th and 5th year, it could have went like that. But because we only know the beginning and ending place, because we only know the beginning and ending place, that's the only way it is. So why do you think dash curves were used? Is because we only know about the actual like dots, And the dashed is kind of our guess, is what we think has happened. So something along the lines of, we only know the dots, the dashes are assumed. Hopefully that makes sense, what I've said there. Anyway, right. If you don't like any of my answers, all the answers are there again. Let's see what they said. A dash curve was used to illustrate that the population is not increasing continuously. Yeah, it's really the idea of, well, that's a silly answer for this one. I really think that my answer's better, so we'll leave it on there. But as long as you've got something that makes sense, who cares? Okay, Maddie, play you have a go. You go, then I'll read it. Okay. Maddie plans to purchase a new PlayStation 5 video game system. He decides that he'll put away $20 every week until he has enough to purchase a console. Each week, Maddie records the total amount saved. Two variables in a resultant relationship are the number of weeks passed and the total number of money saved. Just in case you're not completely clear what's happening here. Let's say we have a table, right? We have weeks happening here because, again, it's time. And then we have money. With 0 weeks, we're going to assume he has no money. That's supposed to be a 0. In the first week, he's going to add $20. In the second week, he's going to add $20. It's going to get to 40. In the third week, he's going to go to 60, right? So hopefully you can see this is what the table would look like. Does the total amount saved have a positive rate of change or a negative? Well, weeks are going up, money's going up, so it's positive. Is the rate of change in this example constant? Yes, it's going up by 20. Yes. Plus 20. Identify which variable is dependent and which variable is independent. Again, independent is weeks, dependent is monies. Monies isn't real English, I'm just being fun. Okay, have a go. Okay, it says the graph on the right describes the height of the ball after it's thrown straight up into the air. Over what time interval is the ball's height increasing or decreasing? So the ball's height then is increasing up until 1.5 seconds, and then at 1.5 seconds it's stopped, and then after that it's decreasing, right? So 0 to 1.5 it's increasing, and then 1.5 to 3 it's decreasing. And on 1.5 exactly, it's going 0. And that's quite an important thing to understand for later. What unit would be your rate of change? Well, it's independent per dependent, so it's meters per second. Over what time interval is the rate of change height positive, negative? Explain. Is that not the exact same question? The exact same as this. Exact same as this, where that's positive going to 1.5 and then negative going down. As the ball gets higher, what happens to the rate of change? It's decreasing, isn't it? As the ball gets higher, the rate of change is decreasing. We've talked about this in a few other questions, but increasing looks like that, decreasing looks like that. And as you can see, it's got that kind of decreasing motion there. What is the ball's rate of change at 1.5? It is 0. It is a flat line. If you zoomed in close enough, it would be a straight, flat line. What are the dependent variables? Independent is going to be your seconds. Dependent is going to be your meters. I am sorry if you can hear me. I'm in the staff room. It's just very loud out there today. Okay, last 2 questions, I think. Last 3. There's 4 questions. So we'll go to the last 3 questions. Have a go quickly. Okay. Order the following from least rate of change to highest rate. Words are hard. So what's the rate of change happening here? Well, this is look at the axis for this, because it's a very interesting question, and as we look later, the axis will change. But the axes are all the same here. So all we have to do is just look at what is the steeper hill. So this is the least steep, isn't it? So let's call that number 3. Hold on. This is the least steep, then this is the next steep, and then this is the most steep. And if you're not comfortable with what I mean by steep, imagine which one of these you'd want to climb. 3 is probably the easiest to climb. 2 is not that easy to climb. 1 is horrible to climb. Lyell claimed that when comparing constant rates of change in all graphs, all that needs to be considered is the steepness of the line. Is Lyell's claim correct? No, because that is the same steep as that, right? So are they constant rates? No. So you have to be careful, because they've both got the same steepness, but this is positive and this is negative, so that's a whole different conversation, isn't it? Okay. For each relation, state whether the rate of change is constant, no constant, increasing or decreasing. Let's just blitz through this. Have a quick go. Okay. So we're just going to first of all go through what's constant and not constant. So I'm going to put constant, not constant, constant, not constant, 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 not constant, not constant. Effectively, straight line or not straight line. Then let's go through it saying positive or negative. This is positive, it's going up. It's positive, it's going up. Negative, going down. It is positive, but it's decreasing. So, I guess that's what it wants, increasing or decreasing, sorry. So, constant and staying the same. Constant, but increasing. Let's put increasing. Actually, let's. I didn't read the question carefully. And that's why it's always important to read the question. That's my fault, sorry. Let's have a quick go. Oh, no, come back. Just remove everything to make sure everything makes sense, because I'd normally edit this out, but the video's been so long already, I'm not doing it, and I'm sorry. Okay, here we go. Right. So, second time's a charm. So, state whether the rate of change is constant, increasing, or decreasing. So, this is constant, this is constant, this is constant, this is constant, and that's it. For the non-constant ones, are they increasing or decreasing? This is increasing. This is decreasing, isn't it? Because it's starting to slow down. This is decreasing because it's, well, it's actually, it's decreasing because it's starting to slow down. And then this is slowly increasing because it's going up. It's technically decreasing. Well, it's going down, decreasing, but it's decreasing to an increase. And this is increasing, but it's slowly slowing down. So it's a complicated one, that 13. Let's see what they said here. Decreasing E, what did I say for D? Yeah, decreasing. And then what they say for H, increasing. I was going to say that as well, yeah. This one's not decreasing, it's increasing. Because it's like, it's going really, really slow, negative, and then it's like going up, isn't it? So like, let's say it was like, the rate was -5, then it got like -3, -2, and it's slowly going towards 0. So it is slowly increasing. And we're going to assume it would keep doing that until it would come back up, which is why you think it's increasing. Okay, and then last but not least, it is the last but not least, the graph on the right shows Pietro's distance from school, D during lunch. Have a quick go. Okay, during what intervals was he moving away from school? It again is 0 to 20, right? 0 to 20, and then 25 to 40. During what time intervals was he moving towards school? We're going to say 55 to 65. And that is it. That's me done. That's probably the longest video I've ever made in my life. I hope you have a good day.